Morning, students. It's Wednesday, May 6th, 2020. Time for some earth science. So today, what we're going to do is we're going to look at differences in magma in terms of mafic versus felsic. And those are terms we've heard before. Mafic and felsic refer to rock properties. We can also refer to magma properties because magma is just liquid rock. But the differences in mafic and felsic are going to lead to different types of eruptions, and they're going to lead to different types of volcano shapes. So we're going to see how those are all fit together today. So let's review a little bit about magma and lava. Remember, magma and lava both refer to melted rock. Magma is below the surface of the earth. Lava is out on the surface of the earth. Mafic is magma that's low in silica. Okay, so silica is a specific mineral. It's got silicon and oxygen. Okay, mafic magma doesn't have as much of that. Okay, it's lower in viscosity. If it's mafic magma, it's lower in viscosity. I'm going to have you look at viscosity in just a bit. But what it means is it flows more smoothly, more easily. Felsic magma is higher in silica. It's got a higher viscosity, which means it doesn't flow as easy, and so it's going to tend to build up pressure and sometimes be explosive. So here's that term viscosity. It's the resistance to flow. So something with low viscosity pours and flows easily. Example, water. Or here's some vegetable oil. Now, I am not certain how well this is going to show up on the camera, but I'm going to try it. In this test tube, I have it full of vegetable oil, and there's a little white marble here. And when I tip this over, the marble takes 1001. It takes about a second, 1001. About a second for that marble to go from one end to the other. Here's a tube that has some motor oil. Okay, again, there's a marble in here. Hopefully you can see it in the camera. And if I tip this over, 1001, 1000, almost 2 seconds. 1001, 1002, about 2 seconds. 1001, 1002. Okay, so what happens is, in order for that marble to move through here, it's falling through, and the liquid has to flow around it. Well, this liquid doesn't flow as easily as the first liquid. So this is more viscous. It has a higher viscosity. Here's one with a higher viscosity yet. 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 1010, 2011, 2012, 2013, 2014. Okay, I counted to 14 seconds-ish. That's a lot slower, a lot more viscous than the other ones. I've got one more. I turn this over, 1001, 1002, 1003, 2004, 2005, 2006, 2007, 2008, 2009, 2010, 2011, 2012, 2013, 2014. You know, that's as long as it took the last one, and it's only gone that far. So, very, very viscous. Now, I want you to picture you have a glass full of these and a straw. And you put a straw in the one that's not very viscous and you blow. You make some bubbles. Now imagine you had the really, really viscous one. I'm thinking that you'd have to blow really hard to make any bubbles. And when it finally gives way, you might have kind of a big splat. That's what I visualize. I haven't actually tried it. That's what I visualize. That's what I imagine. Well, now we got to think about that in terms of lava and magma. in volcanoes. That viscosity is going to determine what happens. So let's imagine we're going to have a volcanic eruption and we have mafic lava. So underneath the surface of the earth, we have a magma chamber. So some sort of conditions happen. Remember, we could have a convergent boundary and have, the subduction zone and melting going on. We could have a divergent boundary where it cracks apart and releases pressure. But something happened that created a magma chamber. And now pressure builds up and we have an eruption. Well, so some of this lava pushes up. But because this is mafic lava and it's not very viscous, it tends to push out and flow to the sides. And so let's say we have another eruption and it flows out to the sides. And we have another eruption and it flows out to the sides. And another eruption and another eruption and another eruption. And it flows out to the sides and creates this very low, broad mound of volcanic rock. Okay? Now, if you were living near this and it's erupting, while this flows fairly easy, it's still usually not flowing super fast. Typically, we can get out of the way. So while it may be a tremendous loss of property, thankfully, these types of eruptions typically don't have a lot of loss of life. That type of eruption is called an effusive eruption, where it flows pretty easily to the sides, pretty steadily. And it's related to mafic lava with that lower viscosity. So these things are related. Okay? The shape of the volcano, low, broad volcanoes, those are referred to as shield volcanoes. Same thing, shield volcanoes. So I got another slide showing the same sort of thing here. Shield volcanoes, low, broad shape, because this lava really spreads out over a wide area. Okay, so all right, here's Captain America and his shield. So if you imagine putting that shield on a flat surface, it just has a low, broad shape to it. Okay, so when we say shield volcano, that's what we're talking about. So here's a picture of Mauna Kea in Hawaii, and that has a very low, broad shape to it. The Hawaiian Islands are shield volcanoes. Mauna Loa, Mauna Kea, Kilauea. They are the result of mostly mafic type lava flows. Effusive eruptions, shield volcanoes. So, what if you have felsic lava? So again, let's start out. Here's a magma chamber. Something has happened that's melted a bunch of rock. And pressures on the earth are squeezing on this and it squeezes up. Now, if this is felsic lava, it's got a much higher viscosity. So it erupts, but it doesn't flow very far before it cools. And it erupts again, but it doesn't flow very far. It erupts again, it doesn't flow very far. And it keeps erupting and flowing, but not very far. And it piles up. You know, when it erupts, it may blow out the center of that cone sometimes. And if you went down to, a second grade classroom or something and asked a kid to draw a picture of a volcano, they'd probably draw you, something like that. And that's what this guy tends to look. It gets very steep sides because the lava doesn't flow very far. And it gets very tall, incredibly tall, big, powerful mountains. There's other problems with this. Because this has such a high viscosity, sometimes this stuff, it's trying to push out, but it can't. So it builds up pressure, and it builds up pressure, and it builds up pressure until the side of the mountain might just blow off. And it might throw all sorts of stuff up in the air. And imagine if there's a lot of gases in here, and you have melted rock and you have gases with it, and it all blows apart, and that rock cools off in the atmosphere into little pieces of very, very fine powdered rock. That's called volcanic ash. And it's still incredibly hot. Okay? Even if it's not in a molten form, it could still be several hundred degrees. So imagine that falling down all around. That's a really dangerous thing. So, all right, we got felsic lava. It doesn't flow easily, so it piles up into tall volcanoes. Felsic is very viscous, it's thick, it's sticky. Okay? And so what can happen is, because it doesn't flow easily, it can build up pressure and lead to explosive eruptions. So the mafic lava dealt with effusive eruptions. Felsic sometimes is explosive eruptions. All gives way at once. Now, the shape of these tall volcanoes is called composite volcanoes. Composite, C-O-M-P-O-S-I-T-E. They are also sometimes called stratovolcanoes. So, some of the same information, those tall volcanoes, composite volcanoes. That's that classic volcano shape that we often think about. But they are much more prone to explosive eruptions. Back in 1980, I would have been in middle school at the time. Mount St. Helens in Washington blew, the side of the mountain blew off. Going from memory here, I want to say I think 56 people died. It was hikers out on the mountainside. Huge area that was destroyed, and that's actually, as far as volcanic eruptions on U.S. soil, I think that was the biggest loss of life that we've had on U.S. soil. That was an explosive eruption. It blew off the whole side of a mountain. Here's a picture of a composite volcano in the Philippines. Very tall, steep sides. All right, so this is just reviewing then explosive eruption versus effusive eruption. Effusive eruptions are, because of the mafic magma, they're kind of steady, slow. They keep pushing out the lava. Again, it may be a lot of destruction to property, but they're a little bit more easy to get out of the way. Explosive eruptions are very violent. The energy can be released all at once and throws this hot matter out, and if you are within the fallout zone, you're going to have some trouble. And that's a result of the felsic magma being very viscous. So another phenomenon happens, and this is associated with the explosive eruptions. It's called a pyroclastic flow. And as far as like loss of life potential for volcanoes, this is probably one of the most dangerous parts. What happens is this volcano, has an explosion. It blows its top, and it releases all this superheated gases that are trapped in that volcano. And those hot gases, along with all the ash and bits of lava and everything, go rolling down the side of the mountain, and they basically incinerate anything that it catches up to. Now, they're very fast. You can't outrun that. Very destructive. This is a picture of a pyroclastic flow in the Philippines. And it looks like you just have this smoke rolling down the mountain. But you have to understand that that's not just smoke. That's bits of rock and ash and magma and poisonous gases. And it's all at several hundred degrees. And incinerates everything as it flows down the side of this mountain. We're almost done with today. I'm going to just mention cinder cones. So we've had shield volcanoes and composite volcanoes. Well, cinder volcanoes are kind of, they're actually the most common volcanoes. But really, cinder volcanoes and stuff, or cinder cones, are part of the other volcanoes. Because when the other volcanoes are erupting, you get places where it's called a vent, where it throws material out of the ground, and that material just kind of piles up alongside and builds this little cone. But sometimes that material is just kind of a fairly loose pile of rock and ash, and when that eruption is done, you have this little cone there, but now weather comes along, rain and wind and all that kind of stuff, and constantly is changing these things. One big composite volcano may have lots of cinder cones around it. So these are kind of small, relatively small, loose piles, relatively temporary. So an eruption happened, you have this pile, and later on it may move around. It may get kind of erased from the landscape again. These are the most common things that people would see, are these little cones. So here's an example of a cinder cone, and just it's kind of this pile of stuff that's gotten thrown out from this volcanic vent during an eruption. There is another type of volcano called a supervolcano. Very large, very rare, and the concept here is that there's a huge magma chamber in the earth, and it basically erupts in one catastrophic explosion. Yellowstone is a supervolcano. Now, Yellowstone hasn't erupted in a long, long time, and while Yellowstone is active, there doesn't appear to be an immediate threat of that. The chances of Yellowstone erupting on any given day are pretty low. I don't know much about supervolcanoes. Your book doesn't say much about supervolcanoes. We're not going to go very far with supervolcanoes. There you go. That's the rest of the material that we're going to get on volcanoes. You're going to have some reading things and a worksheet to fill in. Take care.